Sorry I'm a little bit late. So today I want to talk something about my experience in writing a microkernel in Rust. So I guess this is how I will schedule my talk. So just make sure you come into the right room. So just give first I will give a brief introduction about monolithic kernel and microkernel, and then talk about this specific kernel. I call it Rex, the kernel data, and then I give some implementation details, especially about Rust, and then why microkernel haven't been successful, and if you insist, if you want to write your own microkernel, some advices, and that's it. So I guess in the beginning, just show you a quick demo. I don't have the laptop connected, so this is how it looks like. You try make it, and then it will run your kernel virtual machine, and then it says, yeah, the kernel did not crash. So, do you want to watch it again? Okay. So basically you just open a virtual machine, and this one says, yeah, the kernel did not crash. And it actually might do some basic memory management, and also point things to the VJD. So just give a brief history of the monolithic kernel and microkernel stuff. So in the beginning, in around 1980s, people are still in the research field. People are still writing a lot of monolithic kernel. But at that time, there is also a lot of device drivers, file systems, and polygon stacks being developed. So as a result, it creates a lot of code management problem, because all those things are put into the kernel in the kernel mode, so they can do whatever they want. And if they crash, basically the kernel does crash. And yeah, drivers will crash the kernel. It still happens today. Like nowadays, if you use Linux, you will know that some drivers are not properly supported. So, for example, if you use Broadcom wireless, when you resume from suspension, it will randomly crash your kernel, and it still happens to my laptop. So that is a lot of challenge to this monolithic kernel. And back in 1980s, CMU developed the first, one of the earliest, I don't know whether it's the first, microkernel called Mesh. So, and then GNU packed this microkernel into a full operating system called Port. So you can still find this Port packed Gentoo and Arch. It's called Arch Port distribution nowadays. And researchers are pretty excited about those kind of microkernels. So actually, at that time, in 1990s, you can hear some voices saying Linux is obsolete. So they think Linux is a Master Linux kernel, and it is basically not really exciting to talk about. So this is a mail posted in a mail list from Andy Vulnerable. I think that's what it's called. So you can say that he's a real job is a professor and researcher in the area of operating systems, and he's the creator of the I don't know whether it's creator, but he works on the Minix microkernel. It's also a microkernel. You can find it's a very educational kernel. You can work with it, and he basically says microkernels have one only real argument for most Linux system was performance. And there is not enough evidence showing that microkernel system can be just as fast as manual Linux systems. That is not over, but the shorting. And the debate goes on and on, but as a result, we don't have Linux being replaced. But actually, there's a lot of microkernel. For example, everybody has their mobile phone. And now your mobile phone, you actually run two operating systems. The first is, for example, Android or iOS. And the other one is a real-time operating system that actually manages the communication to the I don't know what it's called, the phone communication. And if you use the Qualcomm-based processor in your phone, if you own an iPhone, that's the case, then you are using a microkernel called AIMSS. And if you're using Android, there's also some other microkernels in your phone. So, and also there's Linux, I have just introduced, and Hart. And also Microsoft has been long working on a microkernel called Singularity, which is very interesting. They don't use kernel-based and user-based, they use language isolation. So everything is just statically checked to make sure your software don't do stupid things to crash either stress memory, and then that is loaded to the kernel and run the kernel mode. So, and if you ever get a BlackBerry phone, there is QNX. That is actually a microkernel. So, but I mean, the researcher at that time they are working on something called L3, and then it ultimately become L4. So you can say that in 1990s and in the 20,000 years, there are a lot of L4 family microkernels being developed. So it basically they share some similar API and some similar design choices. So and there's SVL4. So that is basically a really interesting microkernel. So they use some formal proof to the kernel that basically says this kernel does what it says. And there is also proof for the design of the kernel. So basically, they can be fitted into either the bell-proof assistant, and basically says this kernel just you can't just randomly crash this kernel. So and the kernel is pretty small. So the kernel is around 9,000 lines of C and 600 lines of assembler. So and it really works, and it's reasonably fast. So okay, so that's I'm actually say if you have any questions, just ask in the middle, because those materials actually build on top of each other. So if you get lost, I know that maybe it's hard to catch up. So so maybe I just talk a little bit about the microkernel I'm working on. I call it Rex. And how many of you have taken the operating system class university? Well, a lot of. So I think I can just. It really reduced my. So if you're working a monolithic kernel, you will run those like virtual file system, IPC file system, and scheduler, virtual memory, device drivers, departure, everything in kernel mode. So the application to a system call to this kernel, and the kernel dealt with it, and then return something to other stuff. But for a microkernel, you only get basic inter-process communication and virtual memory management scheduling, and those device drivers and file server, and for example the Unix server, that is the server that handles all the standard library, all run in the user mode. So if you want to, for example, if this application wants to fetch a file, it sends the IPC to this file server, and this file server probably needs to send another IPC to the device driver, and the device driver return to the file server, and the file server then return back to the application. So it's you can say there is a lot of kernel user mode switching, and in a lot of architecture, those kernel user mode switching is relatively slow. So that's the problem microkernel had and now still having it.
Yeah, I just want to ask, so just now you mentioned that if the driver are in the monolithic mode,
Yeah.
and then the kernel will also test.
Yeah.
I remember that I also have the broken issue like yours. Like I thought after I suspended and then I found that the broken driver failed. But it is still running fine, with just without the Wi-Fi other things. So that means the kernel is not failing.
Yeah. So sometimes it will like run the error message or some error, but Linux is pretty smart. It can like recover from that. But I mean, you still get a chance because you are running the driver in the kernel mode. So this driver can do whatever they want. They can access any memory they want. So if the driver is doing something stupid, then you basically the kernel will. It may not crash, but I mean some application may not run right. So yeah. So and a ground author says something about the microkernel. So basically what needs to be inside the kernel is abstraction of hardware address spaces, because that is how you isolate different memory space. You need to isolate them, otherwise an application can just randomly run on top of another application's memory address, and that would cause problem. And you also need an abstraction of execution on the CPU. This is basically to make the CPU to share time, so different threads or different tasks can share the execution. And because you have isolated those tasks, so you need a mechanism for communication across protected boundaries. You need to communicate between those isolations. So in microkernel, that is basically the inter-process communication. And what is actually more, because you actually need to talk with outside world, so you need some hardware primitives. Like you need to be able to talk with the I/O port or other crazy stuff. In x86, there's a lot of this crazy stuff, so you need those things. And there's actually, in Zenly, there is something that can be done in user mode. So this abstraction of execution on the CPU, it can be replaced by just a delegation mode. So if I run as some thread, I delegate my time to another thread. So this is basically saying that you can run the scheduling process in the user mode rather than in the kernel mode, although it may be relatively slow. So it's actually those things. So the ability to talk with the outside world, the hardware primitives, and you need to get resource isolation. So you need to isolate different memories and things like that. And as you have isolated them, you need a way to communicate between those isolations. So here is basically talking about Rust design. So it only supports x86, 64, and in the kernel you need to have this memory management, and you need to have basic task scheduling, and also you need to have no interrupt, and the most important thing actually, and also hardware primitives. So So one way alpha family kernel, including Rust and IC alpha, achieve this is through a thing called capability. There is a lot of research about this, and they basically say if you design microkernel, go capability. So you see there's a lot of types of different capabilities which I will introduce later. The untyped memory capability, which represents free memory, and the page table capability, I will introduce later about the virtual memory thing. So we need a page table, and also page managed capability. You may want to map a page into your virtual address, and those things need to be managed. So there's a capability pool, and also kernel reserve page and bounded page to currently just for this stack overflow, just you don't overflow the stack. And we also have the thread control capability. And unfound capability, this is for the IPC. And also VGA before that is basically now how, this is a hardware limited capability. So you basically need to write text on the VGA before. And also other special IPA capability, for example, timer IPC capability. That's basically if the kernel receives a timer interrupt, that is basically how the preemption works in kernel. So you receive a timer interrupt and you switch to a different thread. So if the kernel receives a timer interrupt, it will give the control to a thread who owns this timer IPC capability, and then that thread can decide whether it wants to delegate that CPU time to other threads to manage scheduling, and etc. other things I haven't designed. So yeah, most important thing is untracked memory capability. So it's actually a pointer with other information to a memory address that is free memory. So it don't have many usage of itself, but it can be retyped into smaller region and of other capabilities. So you can create more useful things from that. And yeah, I think I need to talk a little bit about the memory. So you get the physical memory that is really easy to understand, it's just a number. And you also get the virtual memory. So virtual memory is really important for resource isolation. So in x86-64, basically how it works, you get 4 different pages. This is, I use different name here. This is actually called something like page directory pointer table, and this is called a page directory table, something like that. And then this someone is actually called a page table, and then it is referred to the actual memory. But anyway, I will call it P4, P3, P2, and P1. So in x86-64, you actually only get 47 available addresses, and you actually get 64, but all the other bits needs to set exactly the same as the 47. I don't know why. But I mean, when you first get this address, the first 9 bits will refer to an entry, so the P4 table. And the P4 table is fetched from this CR3 register. And when you get this P4 entry, it will refer to another P3 table. And then this 9 bits will refer to an entry in this P3 table, and so on. So this P3 entry refers to a P2 table. And then this 9 bits sets the offset of this P2 entry, and then P1 entry refers to a P1 table. And then we get a P1 entry, and this P1 entry refers to the actual memory. So you get this. And each memory page is 4K in this specific architecture. So you actually need this So when you allocate memory, even in kernel mode, you need to manage virtual memory. And when you get this, so we need some page managed capability. And a page managed capability are bound to one or more pages. So it's a pointer that pointed to a reserved memory on an object that can be accessed. So when you want to access this memory, you need to first map this page. And then, of course, you need to use this capability to map this page. And when the page is mapped, you can access the object. And when we do the mapping, we need a page table because you see here we need to create some page table to actually create this mapping. So you actually need a page table, and which is a page table is also 4K, so it's actually just another page. And the access method is a little bit different. So you can say that in here it is not part of the page managed capability, it's a separate one. So you can use a method called recursive address, which is, I think it's just for x86, 64, but I will not introduce here, it's not the main point. And when a page is mapped, the page table capability is reference counted. So just to make sure the page is not being accidentally just untyped into a free memory, and we still get some page mapped into here. There is also thread control capability. So it represents a thread, and it owns this thread also owns a capability pool capability. So you get a list of capabilities that this thread can use to make kernel calls. So if you don't have a capability, you can't do the kernel call. So that's how this microkernel implement resource isolation. When you want to access some kind of memory or other things that the kernel values, you need this capability. And this capability is stored in this thread capability pool. And you need to have this pool to fix the capability so you can make the kernel call. So so I think that's about the capability, and I think to give everyone a better understanding of how this capability works, I will just a little bit introduce how the kernel bootstraps. So we won't talk about bootloader here. That is another really big topic. For example, in x86-84, you get some really credits in like A20, and you need to switch from 32 bits to 64 bits, and that's another really annoying thing. And you also get this global description table. I don't really want to talk about that. But I mean that is another whole topic about bootloader. But fortunately, there is some really good bootloader like grub, and we can use that to just load our kernel. And it will also give you a good information about this your memory mapping. So
you use grub in your code?
grub. Yeah, the grub will load my kernel. So it's basically I will put my kernel into a barrel file, and then I put that barrel file together with the grub into ISO, and then I simply load that ISO in that virtual machine. So the virtual machine will first call grub, and grub will then load my kernel. Yeah. So in the beginning, this is also something really frustrating, but I mean, in 60-bit mode, you need to have virtual memory, but you need some memory to manage other memories. So that's a little bit of chicken or egg conflict. And so there is actually some VLAN in the beginning that just identity map the first 1 gigabytes. And the kernel will be logging a specific location in that first 1 gigabytes. And together after that, there will be the boot information. So you need to actually, so this part is really frustrating, but fortunately it was passed. So, and the memory space, you don't have any information about that memory space. So at that time, I basically create an untapped memory capability for the whole memory region. And the kernel was there. So this is now the actual address for presentation purpose. So the kernel may be mapped, maybe at like this position, and then follows that there will be some boot information, and this will be 0, 0, 0, 0, 0, 0. So all those here is just free memory at the booting. And there is a little bit things that contain something that the hardware needs. For example, the VGA differ that is here, that is not free, you can't use that. And there's also some free memory in the beginning. This is based on you have less than 1 gigabytes memory available. So if you have more than 1 gigabytes on this 1 gigabytes range, there will be another reserved memory area that you can't use for some hardware thing. But actually, fortunately, the boot information already gives me all the things I need. So it will tell me in the beginning there is a memory region that is free, and then it tells me this is reserved, and it tells me where the kernel starts, some ELF information, and then it will send me the like an address of where the boot information actually is, and inside that boot information I will get like how long the boot information block is. So and after that it tells me that there is a large free memory area, and probably if I get more than 1 gigabytes memory, it will tell me there is also a region that is reserved, and also free memory after that. So yeah, it first creates this untapped memory. And in the beginning, you only get a kernel stack, so you put this capability in your stack. It's very small, it's just a pointer plus other relevant information. So yeah, then the kernel found the boot information structure, and it finds all the addresses of the boot information and the kernel itself, and it retypes this big untapped memory into some small reserved kernel page for this boot information and kernel itself, and also I get other untapped memory. So yeah, so at this point I know other memory addresses are fully free. I can use it whatever I want. So I create a capability pool using those untapped memories. So and this capability pool capability will actually create a capability pool in some region of the memory area that I know is free because I have this untapped memory. And then yeah, it needs to do some messaging with the new page table, but let's skip that. It's very messy. And it then switch to the new page table, and then map the capability pool capability again. And then it just transfer all the capability on its stack, except those except the capability pool capability into the capability pool. So now I have a capability pool that is owned by the kernel. And you set that capability into some static variable in the kernel that is in the kernel reserved area. So and because the kernel owns the capability tool, so it access to everything. Yeah, and then the kernel needs to run some other licensing. This is not implemented yet. So and after that, because now I know the kernel don't need to allocate more memory because this is a microkernel. And after bootstrapping, I know all the memory I need to manage is actually managed by a particular thread. So I can pass all my untyped memory into my first thread. So let the thread to manage all the capability. So I create a thread control block capability, and I create another thread pool that is owned by the thread, and then I pass all the untyped memory and other hardware primitives and all other important information into that thread capability pool. So now I can hand over to the capability to the thread, and let the thread manage all the other things. So the kernel is basically bootstrapping and then wait for interrupts and to send specific events to different threads and just maintain those resources isolation. So this is not implemented, but just give a quick overview how scheduling may work in this kernel. So we get those timer interrupt, and it's treated as a normal interrupt. And in alpha family kernel, those interrupts are actually treated like an IPC. So I send this IPC into a thread that has some specific capability, like the timer IPC capability, and then it just gives all the control time control to this specific thread. So this thread now have everything all the time. And yeah, if nothing happens, that thread can execute until next event happens. But if this kernel actually works, if this operating system actually works, and this scheduler acts as a powerful scheduling server, it then will delegate its time to other threads. So it will select a thread and then call the delegation. So that's how scheduling works. And IPC is basically work like this is also not implemented. So you get a really small IPC, and all those IPC information is stored in the registers. So in this way, I can just the kernel a thread store those store my IPC information, a message into its registers, and then do a kernel call, and then switch to kernel mode. And the kernel just check whether those registers are correct. And then it can just not changing those registers, but just switch to a user mode for another thread. So it just finished an IPC. That is actually one of the fastest way that you can do IPC. But yeah, but my kernel is slow. Yeah, and if you want to send something big, you need to send over to memory capability. So you transfer capability into another thread. So that is basically avoid kernel copying information. And yeah, that's basically all the design information I have. And the IPC and scheduling is actually not implemented, but I plan to implement in that way. And probably I will give some implementation details about how things actually works in Rust.
So wait.
Oh, this is some render paragraph from a book called the Rust CUHKOIL. So it's about how to write unsafe Rust code. Yeah, so Rust, if you don't know, is a programming language that has memory safety without garbage collection. That is very appealing to me. And it tries to achieve zero code abstraction. I don't know whether it really did that or not, but it tries to do it. So in Rust, there is a really important idea called ownership. So you can actually think about ownership as a hierarchy that, for example, you own some, the main function owns some variable, and that variable also holds another variable. So ownership basically says in that hierarchy, you only get exactly one pass to a specific to a specific variable. So here, if I got a struct which is full, and I initialize this struct to a variable, and then I assign var to full. So now if I do something like this, it will tell me there's a error because full is now moved. So in Rust, each assign actually have one more meaning. It transfers the ownership. So if in the beginning this full is owned by full, and then in the second assign, you transfer ownership from full to var. So you can't access this full anymore because it's full. But you can actually make a reference of this full. So a reference is like you create a name of that path. So you can have multiple names. But there's also some function that basically tries to make sure that other rules that basically tries to make sure you don't mess up with things, create like data write or other things. Yeah, so you get unique owner path, and you have reference, and you can think of it like names or owner paths.
I have a question. So if you use reference, how do you still have thread safety?
Yeah, that's a really good question. We don't have thread safety in kernel because this kernel is non-preemptive. That means if there is the code is running in kernel mode, it can't just receive another interrupt and enter another kernel mode like that. You need to finish the current kernel mode and then enter to another kernel mode. So there is always like this kernel is running in a single threaded thing. So you don't have thread safety.
Actually, I think if I use Rust, and then I also want to use reference, then Rust won't promise. In Rust there is a trait. It's called trait. It's like a type class. So it's called sync and synced. So you can use those traits to create thread safety. So it gets this support, but we won't use that here. I don't know much about that either, but I think you can just check about the thread safety of Rust. It's probably supported, but it's not used in this kernel. So this kind of ownership actually influence some of the design of the kernel, because basically the original design of this unchecked capability is to just retype the memory and then create a hierarchy. So, but in that case, it would be just really complicated to deal with the ownership, because now you can access each capability in two ways. You can access it through the capability pool, or you can access it through the hierarchy. You get an untapped memory, and inside that you get some children that is, for example, page managed capability or other thing, and that just complicates things. So, and
this is the first time I read a microkernel, so I just want everything to be simple. And so this doubly link actually creates a lot of problems. And if you're interested in this kind of problem, maybe you may want to look how Rust implement double linked lists. It's really interesting how they use unsafe Rust to do that. And there's some people who try to just use safe Rust to create this double linked list, but it's not as efficient as our low implementation. So for the capability pool capability, and when you take a capability out of a pool, you get its ownership. And at that time, I also free the Arnold pool slot.
So at that stage, you actually clone it?
Was it?
Do you clone it?
I don't clone it. I don't clone a capability. Because clone a capability will make it unsafe. If I clone that, that means there is a chance that two...
So you transfer the ownership?
Yeah, I transfer the ownership.
Completely?
Yeah.
Okay.
So basically, the capability pool is that is basically a lot of unsafe code,
Yeah.
and then
Yes.
you will get it out, and you say you have the ownership. And you take it in, you also enter a lot of unsafe code. Yeah. So yeah, when you put the capability into a pool, you lose in ownership, and yeah, you can't operate on that anymore, and yeah, so that will also enter a lot of unsafe code to just make things work. So the capability pool actually has a lot of row pointers and things like that, and that is, yeah, that is a lot of headache. So yeah, so for the page table capability, you only put the so a page 4 table owns only student, and a page 3 table owns only student. So that's basically how it works. Yeah. So yeah, so in Rust they call it stack and heap. I don't know whether I use heap here because it's a different concept, but it's actually dynamically allocated memory. So you get all those variable and function parameters on the stack. That's how C and other language works. Is also same in Rust. And others, for example, vectors and other things are dynamically allocated. So you have a lot of so about unsafe Rust, and when you're working with something not in the stack and that's on the heap, and you don't have the access to the standard library, that's basically what happens when you write a kernel. You can't use the standard library. So in that case, you need a lot of unsafe Rust. But you better make sure you still obey the ownership rules, because those unsafe Rust need to interact with the safe Rust code, and you may leak memory or do some other thing that you don't want. Yeah, in Rust is currently mostly in those memory management activities. So this is something fun. So this is how a VG before works. So when you enter the kernel, there's a VGA before at this location E8000, and you can just grab that row pointer and just do something and say get this mutable variable, which is actually something like this. There's a array of charts, and this width, if I remember correctly, is 80, and this height should be 25. So you just set a specific chart to a string chart. That is basically, in the first you get some byte, or ASCII byte, and after that you get some color code. So that's how you say you get yellow color on that in the beginning of the video. Yeah. So yeah, that's all the implementation. And maybe I want to talk a little bit about why microkernels still haven't won. So it's mostly First is because people they just get used to what they already have because Linux and other kernels already working great. Why do you create another kernel? And another thing is about IPC performance. So if you look into this graph, this is Minix. That is one of the earliest microkernel. It's actual operation transfer rate. So you get this size to this rate, and I think this line should be the Linux kernel or other mono-Linux kernel, and this line is the microkernel. So I think in this way it seems pretty thin, but if you look at this graph, you can see that well something in Linux is very, very fast, but if you do that in Minix, it's really just really, really slow. So when they first implement mesh, they found the problem, and it is actually still a problem now, because if you say here, you can say just in the alpha family, the microkernel performance is not really improved because switching between kernel mode and user mode is actually an architecture-related problem, and that is, I mean, you need to, if you want to make that fast, you need to, if you want to make that fast, you really need to change the architecture. So you say, this is not really improved, and this is like the worst one, you know, why it takes 2,000 seconds, and this is the quickest one. Yeah, so it's another alpha family kernel called Pistachio, something like that. And yeah, so the argument is basically is slow, and there are also design flaws in microkernel. And yeah, because people later say they don't solve my problem because my Linux runs great, and they just don't care about like my laptop randomly crash. And if you insist to run a microkernel, this is the first advice: don't run microkernels because it really takes a long time, and it's addictive. So if you get into writing the kernel, you just want to work on the kernel and ignore all your work tasks. So, but if you insist, so here is how I did all those things. So first you need to understand you're writing a kernel, not a bootloader. So just it is not actually the case. You need to make all those things understand exactly. But I mean, if you use grub or other bootloader to bootstrap your kernel, you save a lot of work. And why don't you do that? So and then you can copy some code from the internet. There's a lot of people trying to create their microkernels, and a lot of people trying to create their microkernels in Rust. So and when you can write a hello world to the screen, you actually need to stop and try to design a kernel how you want it to work, because in a kernel, everything is entangled, and if you just try to make one functionality work, you may just break another functionality, and you need to change the first functionality first, and it's really frustrating. So take some time to design a kernel, not just keep writing, and implement your kernel step by step based on your design. And that's as far as I have gone. And yeah, that's it. So this is the kernel design documentation. It's still not finished. If you want to have a look, this is the source code. And yeah, the only part of this design is implemented in the source code, and it may not compile. So yeah, that's it. And thank you.